Good morning and good afternoon, everyone. Welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I will be your host for today. And we've got a great group of classrooms joining us today, classrooms from Canada and the US, as well as more who will be tuning in live via YouTube. And we're really excited to get today's event going. So today we are joined by Laurie Rousseau-Nepton. She's a resident astronomer at the Canada-France-Hawaii Observatory and a postdoctoral researcher at the University of Hawaii. So she was the first indigenous woman in Quebec to obtain a PhD in astrophysics. She received her diploma from the Université Laval by studying regions of stellar formation in spiral galaxies using an imaging spectrograph. She's presently an FRQNT postdoctoral scholarship recipient and previously received the Hubert Reeves Fellowship. So Laurie, it's so awesome to have you tuning in and joining us live today. We're excited to get to know you a little bit better, and then we'll turn the classrooms loose and let them ask some questions.
Okay, awesome. Thank you so much for having me. I'm just so glad to be here this morning for me. I don't know what time it is for you, but here in Hawaii, it's about 9 a.m. I have prepared a nice presentation for you, so I hope you'll be able to enjoy it. And I'm going to start my share screen right now. So I won't be able to see you, but hopefully you see well my presentation here. So I'm an astronomer. I work for a telescope, the Canada-France-Hawaii telescope here in Hawaii. Here you see me beside the telescope and also beside one of the nicest sunsets that I've seen. And so the telescope that I work for here as 7 astronomers that work for it. We have people from Canada, we have people from Hawaii, the US, and also people from France. And we all work together on different topics in astronomy. And before I go into the details, so I just wanted to show you where I am. So it's in the middle of the Pacific. It's quite far from Quebec or any of your location right now. If I want to go back home to see my family, I have to take a couple of flights. But I try to do it every once in a while. And as Joe mentioned, I am a member of the First Nations. Actually, I'm a member of the Pequot-Kamilniwas Nation. It's nearby Saguenay-Lac-Saint-Jean right here. And I go back every year with my family, and we go hunting a little bit further north. And this is just to give you an idea, a couple of images around our hunting camp. And I think my journey all started there when I was young. I was spending a lot of time in the nature, and I love observing things. I love understanding how they work. And physics is the field of study that allows you to study nature and trying to understand that. And astronomy is a field of physics that just try to do the same thing, but for the universe. So we're looking up and try to understand how things work up there. And so at first, my first experience in a telescope was in Quebec at the Montmégantic Observatory. So here are some images that I took there. I spent a lot of time during my studies, my graduate study, observing galaxies there. So here's a picture of me with a couple of other students nearby the telescope dome. And back then, I was testing a new camera. So it was called Espion. It was a very unique camera, a prototype. There was nothing else in the world that was just like Espion. And my job was to make sure that we could observe with it and that we could do science with it. And instead of taking just images like a typical camera, like the one you have on your cell phone, it does something very special. It's splitting the light, just like when you look at a rainbow, the light is split in different colors. So Espion is doing that. It's splitting the light in all the colors. And so I can observe a galaxy and see a nice image of a galaxy. And every pixel of an image would be a rainbow, would be all the colors. So it gives you a lot of more information if you're an astronomer. So we're going to leave Earth. I've stolen a video from the movie Contact. Probably none of you have seen it, but if ever you want to see a nice movie, try to watch Contact. So we're leaving Earth. We see the Earth and the Moon, the Sun, and very soon we're going to see the other planets of the solar system. And I like to show that video at first just to grasp how big the universe is. So of course, the solar system is gigantic. We have huge planets like Jupiter. We're passing Jupiter and the moons of Jupiter right now. But what I think is, oops, just gonna go back here. Sorry about that. So let's go back to Jupiter. So we're gonna fast forward it a little bit. And this is Saturn. And I want actually to exit the solar system. And here we are. So we're leaving the solar system. We see that bubble of comets. And my work, what I do here is studying new stars. I'm not studying the sun or anything close to the solar system. I'm studying stars that are formed within galaxies in the gas, like this cloud of gas right here. And this gas is always creating new stars, and it happens all the time in galaxies everywhere. So there's thousands and thousands and thousands of new stars that are created, and actually here there's probably thousands of stars within that cloud that are being born. And we're gonna again fast forward. I don't know how to remove that menu over here. Let me just start it over again to see if, yeah. Give me just a second. Here we go. Okay. And now we're leaving that nebula, and we're even leaving the Milky Way. So as we move out of our own galaxy, the Milky Way, we see all the stars. There's billions of stars. And then we see another galaxy that is around our own galaxy. It's what we call a dwarf galaxy. It's much, much smaller. And then eventually we're going to go through the Andromeda galaxy, one of our closest neighbor. And we see all the gas and the stars. And as we move out, we see all the galaxies surrounding us. And there's thousands and thousands and thousands of them. And I like to pause the video here, just because we know that that there's so many galaxies around us just for one reason. Because if we were, let's say, an astronaut in space in this exact position, our eyes wouldn't be able to see anything. Those galaxies are actually too faint to be seen by the human eye. And so we know that there's thousands and thousands and thousands of galaxies around us just because we observe them with telescopes. And so we would be in complete darkness without telescopes. So all these galaxies we have observed now within the past hundreds of years with telescopes, and we know how the universe looks like. And so this is what you see with the naked eye if you're lucky enough to be in an area where there's not too much light pollution. Now, if you use a pair of binocular, you might be able to see the Andromeda galaxy if you're looking at it with a pair of binocular. And then if we take a telescope, a very powerful telescope like the Hubble Space Telescope, and we look into one very tiny dark area here, then what you start to see is those galaxies that are farther away. And you notice that they are all very different. They have different colors, they have different shape, different size. And so this is what we're trying to do with the telescopes when we're studying galaxies. We're trying to understand why those galaxies are so different, and are there any that look just like the Milky Way, or is the Milky Way special, or just a normal galaxy, and things like that. And so this is my telescope, the Canada-France-Hawaii Telescope. If you're inside the dome, it looks like that. And I have a nice video that shows how things are moving inside the dome. So here you see the slit of the dome opening before the start of the night. So the sun is still up. We're actually opening the dome right about the moment where the sun is setting, about like an hour before sunset. And it helps getting a lot of the cool air from outside inside the dome. And the telescope really likes to be surrounded by cool air. And if we wait a little bit, we're going to see very soon. Notice that on the side here, you have those little windows. They're closed right now, but eventually they will also open to get more air inside. Here you go. And the dome can rotate, and the telescope can point anywhere on sky. So I think at the end, our observer is tilting the telescope towards us so that we can see the mirror. And the mirror is located right at the bottom here. And it's a very big mirror. It's 3.6 meters, so it's much, much bigger than the human eye. And this mirror is gathering all the light that we need to observe those galaxies. And this is where it's located, on the Mauna Kea. And it's the one on the left. And the Mauna Kea has about 13 telescopes at its summit. It's one of the nicest places on Earth to observe, actually. And this is the island. And this is the big volcano, the Mauna Loa. And aside, there's another one that is really active, the Kilauea. But all the telescopes are on the quiet volcano, the Mauna Kea, right here. And this is something what happens on the island, but don't be worried, it's not really dangerous for the telescopes. They're far away from that. What often happens here is that the weather is not quite nice with us. So this is one of the storms that we got last year. And we still need to observe when the sky is clear, but when we get a storm, we close everything to make sure that it protects our equipment and our cameras. So now this is me in the dome. I'm pushing a huge equipment. It's actually one of our camera. This camera is called CITEL. And this is the reason why after I did my PhD in Quebec, I got hired here, because this instrument is actually a second version of that prototype camera that I was using in Quebec, Espion. So Espion was so good. When I did my PhD, it worked so well that they decided to build a new version, a new generation of Espion for a bigger telescope like the one here on the Mauna Kea. So I got here with that new camera that was built in Canada, and we mounted it on the telescope. This is how it looked like when it's on the telescope, and we started observing with it. And the first time you observe with a camera on a telescope, we call that the first light. And this is when it happened in 2015. And there's a group of people that were all there surrounded by the computers and the control of the telescope. And we were all waiting for the first light to get into the camera to see the first images of CITEL. And at the same time, there was a huge hurricane that was coming towards the island. But we got so lucky because the hurricane turned north right before, and we could observe and have very, very clear sky for a couple of days in a row. So we were really happy. And so there's a group of people that were working at a summit around the telescope. You can see them here, and they were putting CITEL on the telescope. So my work here is to do science, of course, but I'm part of this big group that is taking care of the telescope, and sometimes we have to do maintenance also. So here's an image of when we clean the mirror, and we actually have to remove the aluminum that is on the mirror, that reflective layer. We have to remove it, and to do that, we use acid. And this is really, really intense, and we are wearing masks and a full suit, and we remove that layer of aluminum from the mirror, and we put a new one, a new shiny one that is reflecting the light perfectly well. And so this is an image of me. I wasn't wearing my suit. You can't recognize me, but believe me, it's me. I'm there. And we were cleaning the mirror before doing the acid and the recoating of the aluminum. And this is also a picture of me with one of the biggest wrench that you will ever see. This is the one that is used to unbolt the telescope, which has screws that each screws actually weighs about 10 pounds. And so back to CITEL. So like I was saying, this is the telescope. CITEL is at the very bottom. So what happened when we open the dome is that the light gets into the telescope. It hits the mirror at the bottom, and then it's all reflected into a smaller mirror right here, and then reflected back into the middle of the mirror. If you remember well, there's like a hole in the middle of the mirror here. So the light is reflected here, goes into that hole, and get into my camera. And this is how I gather the light from the galaxies. And so what do I study, like I was saying, is those stars that are forming inside those clouds of gas. And we can observe them in the Milky Way, like this magnificent one here, which is called the Rosette Nebulae. And also we can do something even better, is we can try to simulate what's happening into those big nebulae with computers. And this is actually images from a computer simulation. And I want to show you a video that is simulating in an accelerated fashion what's happening in a nebulae. So imagine there's a really young star in the middle of that gas. Once that star lights up and is literally created from the gas, the light coming from the star is kind of warming the gas around it, and it creates those really nice bubble of shiny gas that we observe. And this is what I am looking for my science. And so why this is important for astronomy, it's because each star is like the sun, is formed through gas, with gas in their galaxies. And this gas can be transformed by stars. So when a star is formed in gas, it is transforming that gas. So our sun right now is burning hydrogen. So hydrogen is a really light gas, and it is actually creating new atoms like helium, like oxygen, nitrogen, and things that are surrounding us on Earth. And so those stars are actually machines that form new atoms. And once they die, some of them explode, and they push all those new atoms around them in the galaxies. And this cycle goes around and around. So the gas that is now enriched with oxygen, nitrogen, and hydrogen and other things is creating, again, new stars that could have planets like the Earth, and so on. So we're trying to understand how this cycle is working in galaxy. So now I'm going to show you an observation from CITEL. So as I was saying, it's an image, but it's also a rainbow. So I can go through the rainbow and create a video with my observation. So this is a video that moves into the rainbow. So we're from the red to the blue, and we see that there's things that are flashing actually in galaxy. And we can zoom in and look at those areas that are flashy. And actually, all of those little points that are really bright are a region where you have newborn stars that are warming the gas. And what we see is the really hot gas around newborn stars. And this is an image that I created from those observations. So it's a galaxy very close from us. And all the big, bright nebulae that we see are actually in an area where you have newborn stars. So we can zoom in, we can see those blue young stars surrounded by the warm gas. And we can even check again the video of that section of the galaxy, which is called Messier 33. And again, you'll see the filaments of gas that are really warm appearing in the video here and there. I'm going to go back where you have actually, yeah, here. So you see all those nebulae are actually region where you have newborn stars. And so I'm just a part of the study of the universe. I'm just studying one tiny little piece of the puzzle. So we're trying to understand how the stars are formed, how they influence the galaxies, and how they influence the new generations of stars that will be formed later on. But in astronomy, astronomers study a whole wide variety of topics, from studying those galaxies when they are really, really far away from us, and also trying to understand how the universe evolved from the Big Bang to today. And so I hope that I give you an overview of what I'm doing, but I hope also you have many, many questions, and I'll be happy to answer them. And if ever you end up doing astronomy or physics, be aware that we're having interns and students that come here to work with us. So this is just a few images of some students that came to work with me here at the telescope. So keep that in mind. Thank you.
All right. Very cool, Laurie. Thanks so much for sharing that with us today. You know, it's amazing how you can peer out into our universe and see these distant galaxies and bring them to life. It's so cool. So thanks so much for sharing that with us. You definitely have a cool job and in quite an awesome location. So a little bit jealous of that too. All right, very cool. Well, let's start meeting some of our classrooms. So let's see, where should we start? Okay, let's go to Mrs. Crouch's group. They are in Smithville, Missouri. Let's get their microphone turned on. There it is.
Hey.
How are we doing, Missouri?
Hi.
Hello.
Hello, sisters. Hello, Joe. Go ahead, ask your question.
How many stars do you discover in a year?
Oh, that's a good question. So I'm studying galaxies that are close to the Milky Way. So if they're really, really close from us, some other astronomers might have already discovered the stars in them. But there's one thing that is really, really nice is that as the telescopes are getting better and better at seeing really, really tiny details in galaxies, we always discover new stars. So it's like you take an image of a galaxy and it's really fuzzy and you can't barely see anything. And then in a few years after that, you tune a little things here and there on the telescope, and then the telescope becomes much better at seeing images very clear. And once you have that new image of the same galaxy a couple of years after, then you see all the stars and actually discover thousands of them at the same time. But you can't really name them. There's just too many. But they don't even have a name.
All right, very cool. Yeah, I like that video you shared at the beginning. Our universe is huge. I mean, the Milky Way alone has billions of stars, and then there's, what would you say? Would you say there's billions of more galaxies after that? And
Oh yeah, there's billions and billions of other galaxies. It's actually so big that our brain cannot imagine. Like our brain is not built to figure it out. Like, but we know that it's big like that because sometimes we can observe galaxies that are really, really far. And we're building always better telescopes, and eventually we'll see even further, and we'll see even more galaxies. We're actually discovering galaxies all the time as well.
All right, so cool. So much left to explore and discover. So astronomy could be a really exciting career for some of the students who are tuning in today. So we have Miss Marriott's class. They are hanging out with us in Vancouver, British Columbia. Let's get that microphone turned on. How are you doing, Vancouver?
Hello.
Hello.
How are we, folks? I don't know if you can hear that or not. It's just shy of 11:30 over here. And if you can believe it, it is actually a sunny day today.
Ooh.
Yeah. It's a cold day. Yeah. Do any of you have a question that you would like to ask? Okay, let's hear right here, nice and loud. Yeah, you. Yeah, you.
What do stars look like up close?
That's a good question. So if we were to go out into space and look at a star instead of through a telescope, what would we see?
Oh, that's a good question. So we see often images of the sun from the satellites that are surrounding the sun. And we can see that the sun is actually really, sometimes really active, sometimes more quiet. Like a star is actually, there's a lot of things happening on a star. And depending on which star you're looking at, you won't see the same thing. So some stars, like the cooler, smaller ones, like some stars that are like 10 times and even smaller than the sun, some of them have clouds. And we can detect those clouds when they pass and rotate around their star with telescopes. So we can't really see an image of that, but we know it's happening. So some stars that are really small and cold have clouds. And then some are just like the sun, and they are sometimes active, so they have what we call eruption. And when there's an eruption, you have basically some particles from the sun that are launched into space. And this is one thing that is neat, is once those particles reach the Earth, it's more likely to see auroras if you're living close to the North or the South Pole, because those particles are the ones that creates those nice northern lights that we see sometimes in the pole. And so if you take, let's say, a larger star, like 100 times as massive as the sun, then the star would be so big compared to the sun. And also it wouldn't be the same color. It would actually be kind of blue. So some stars are like red if they're smaller, and all the way up to blue if they are really, really big. So you could imagine that.
All right, very cool. Good question. Let's go to Marlton, New Jersey. Some students hanging out with Mrs. Milch. Let me get their microphone turned on. There it is. How are we doing, New Jersey?
Well, my name is Mia, and I
Did you catch that, Laurie? It was a little quiet.
No, no, please. Yeah.
So she was wondering about life in other galaxies.
That's a good question. So when we observe other galaxies, we found that some of them are different than the Milky Way, and some of them are very similar, actually, than the Milky Way. So we have like twins galaxies that are not exactly the same, but they have really similar shape, similar amount of stars, similar amount of gas, and they also form stars at about the same speed. So thinking that we exist here in the solar system, in the Milky Way, it's very likely that there's at least one star somewhere in a similar galaxy that has just passed through the same thing, the same evolution as the sun, just got born in a similar cloud of gas with the similar amount of all the atoms that are in our body, in the Earth, and in the solar system. And then some planets might have formed, and who knows after that. But like we're trying actually with telescope to discover planets. Right now we're really good at doing it in the Milky Way. Eventually we'll be able to detect planets, exoplanets in systems that are outside of the Milky Way. But for now the telescope are not as quite powerful to do that.
All right. Well, I think that with the number of stars, the number of planets, I think it's very likely that there's probably lots of other life in places all around us. So I hope we can find that out for sure sometime in the future. All right, very cool. Let's see, Miss Mayer's group, looks like some 6th graders in Vancouver. Let's get that microphone turned on. How are we doing, 6th graders?
Say hello.
Hi.
Okay. Have a seat. Have a seat. Okay, go ahead. Go ahead. Yeah. Go ahead, they're reading.
Hi, Laurie. I'm Lauren. Twin.
Oh, hi, Lauren.
Can you name one nebula or a group of stars?
So one nebula,
Or a group of stars, can you name one of them?
I would pick my favorite one, which is not like, because a lot of people really like that one. It's the Orion Nebulae. So Orion Nebulae is actually in the constellation of Orion. If ever you're able to identify some constellation in the night sky, you can look at the Orion Nebulae. It's like a very easy shape to identify. There's 3 bright stars in the middle, there's 2 all the way up and 2 all the way down. And this nebula is located in the bottom. And you can actually see it with a pair of binoculars because it's so close from us and so bright that a pair of binoculars is enough. And in that nebula, you have a bunch of really young newborn stars. And actually, wait, yeah, I have a picture of it. Give me a second.
You know, stars forming.
There you go. Aha, it's this one. So that's the Orion Nebula. And in the middle there, where it's really bright, you have a bunch of really massive young stars. They're really big, much, much bigger than the sun. And I like this one because when we observe it, it's so close that we can see all the details and all the nice filaments of gas, and we have a lot of things to do science with.
All right, very cool. And now is a really good time of the year. So with winter coming upon us in Canada and the US, Orion will be visible all throughout the winter in the Northern Hemisphere. So it's a really good time to check out Orion if you have some binoculars, or maybe you have a telescope if you're lucky.
Yeah.
Be able to check it out with the telescope. All right, very cool. We're gonna head to Quebec now. We have some high schoolers hanging out with us with Mr. Harvey. Let me get that microphone turned on. Oh, let's try that again. Oh, Mr. Harvey, I might need you to turn it on for me for whatever reason. It's being tricky today. There it is. How we doing, boys and girls?
Can we ask the question in French?
Yes.
Avez-vous déjà vu des trous noirs?
Okay. So the question is if I have ever seen a black hole. That's a good question. Je peux la répondre en français puis en anglais par la suite. Is it okay if I answer in French and then in English, or you prefer English only?
No, both is good. Yeah, it's awesome.
Donc, j'ai jamais vu de trou noir parce que les trous noirs sont vraiment, vraiment difficiles à observer. Par contre, je connais des gens qui ont fait des observations puis qui ont envoyé une image, la première image d'un trou noir. Puis d'ailleurs, c'est des gens d'Hawaï qui travaillaient en collaboration avec plusieurs autres télescopes. Ils appellent leur télescope le Event Horizon Telescope. Et c'est, je crois, 8 télescopes qui sont situés partout sur la planète Terre. Et avec tous ces télescopes-là qui regardaient le trou noir d'une galaxie, au centre d'une galaxie, en même temps, ils ont pu créer une image. Donc, vous pouvez aller voir ça sur Google, là, Event Horizon Telescope. And if I answer it in English now, so I have never seen a black hole by myself, but I know researchers that have used telescope here in Hawaii, and they were actually collaborating with 8 other telescopes around the Earth, and they created that constellation of telescopes that were looking at the same black hole in the center of a galaxy at the same time, and they were able to create an image of it. And this telescope, which is that constellation of telescope, is called the Event Horizon Telescope. So you can go on Google and Google Event Horizon Telescope, and you'll see the image of the black hole that they have created.
All right, that's very cool. So on YouTube, Mrs. Florendo's class is joining us, and they're grade 5/6s in Winnipeg, Manitoba, and they're wondering approximately how far into the universe can you get a good picture with the Canada-France-Hawaii telescope?
That's a good question. So the how far is a hard question to answer because, and I'll tell you why, some galaxies in the very far away universe, so as you look far into the universe, you're also looking back in time. Telescopes are like a time machine. The farthest you look at, then the longest it took for the light to come here. And so the picture that you actually take is back in time. So some galaxies in the early universe that are really, really far then were really, really bright. They were very different than any galaxy you would observe around us right now, because it's like looking at a baby galaxy or a galaxy that was formed in a very different environment. And some of them are so bright, we call them quasar, because when the first time they observed them, they thought they were a star because they were so bright. And they're really, really tiny, so they look like a star. But when you study them in more detail, you notice that it's actually a very, very far away galaxy that is really, really bright. And so quasar was like quasi-star, like a star. So they named them like that. And when a galaxy is that far away, the distances are not even calculated in kilometer or miles. We have other way to calculate distances when they are that far, because it doesn't even make sense to talk about kilometers or miles. It would be like, I don't know, 10, or like a 1 with like 30 zeros, kilometers, or a really huge number. And so therefore, we're talking about the size of the universe at the moment the galaxy was living in, because the universe is expanding. And so if a galaxy is really far away, the universe was smaller. And so we talk about the size of the universe when the galaxy was born.
All right, very cool. So I think we have time. We'll visit a couple more classrooms. So Mrs. Crouch, we're gonna go back to your classroom first. If you guys have another question, we're ready for you.
Stop. If you had any dream to be in like the solar system, what would it be?
Oh, I couldn't hear it, sorry.
What's your dream or wish?
My dream. So I'm gonna talk about like my astronomer's dream. so there are 2 things that I would like to see. So one things that are really rare and doesn't happen often in the sky are when a really massive star dies, it explodes, and we see it as a supernovae. We call them supernovae. And this happens very quickly, and it's really, really a powerful event when a star just explodes. And some stars in the night sky are really massive and could explode. So if I had a wish, I would like to be alive when this happened, and I would like to see it in the sky with my own eye without using a telescope. So there's a few stars in the night sky that could do that. but the likelihood that it happens while I'm still alive is really, really small. So I would wish that it happened during my lifetime. So I would like to see it.
All right, cool question. It's the Marriott's group. Your microphone's on if you guys have another question.
Great. Could I very quickly ask, it's really cool that you speak English and French. Do you know any other languages?
Oh my God. I'm trying to learn a little bit the Hawaiian here while I'm here, but it's really hard. And I have started a little bit of Spanish, but not quite yet. So it's really hard actually to learn new languages. And even learning English was, yeah. But I'm trying also to learn a little bit of the local language. Yeah.
That sounds great. One of my students has a question. What is it?
When you said the universe is expanding, what do you mean by that? Like the universe is getting bigger and we're getting smaller?
Could you hear that?
No, not
She's
quite yet.
asking, what does it mean that the universe is expanding?
Ah, okay, that's a good question. So, usually I have slides for that. So usually if you go back into the first time we had telescope, astronomers look into their telescope and they were looking at for the first time at galaxies around us. And one of the things they first notice is that when you look at a galaxy far away, they all look to go away from us. They all look to try to escape from us. They actually, depending on where they are, they really are moving away. And the farthest you look at, so if you look at a galaxy that is really far from you, then it tends to go away from you faster. So if you look at a close by galaxy, it's going a little bit away. And then if you look at a really far galaxy, it's really going away from you. And when they first observed that, they thought, this is really odd. Why is that every galaxy around us is moving away? And this is how they discovered that the space in between galaxies is expanding. So if there's a little bit of space, it's expanding. So it kind of create that illusion that the galaxy is moving away, which is the case, but it's mainly because the space is expanding. And so the farthest you look, the more amount of space there is in between you and a galaxy. So the farthest the galaxy is moving away from you, the fastest. And so this is how they discovered it. And if you go back in time now, if you try to see the universe when it was really young, then it means that the space was we're closer actually to other galaxies. And so you can go back in time and try to figure how it was looking like. So this is how they came up with that theory that everything was all together in one point. And then the universe must have started expanding. And then it is still expanding today as we observe it. And it's even accelerating, but we don't know why. It's a mystery. It's one of the mystery actually that astronomers are trying to figure out.
All right, very cool. Mrs. Mayer's group, let me get your microphone on if you guys have one more.
Oh, good. Yeah. Go ahead.
What interested you into astronomy? What interested you into astronomy?
Okay, yeah. So that's a good question. So when I was a student, before even going to the university, I was like really good in chemistry. I was kind of okay in physics, but when I was following the classes, I was so much more interested in the physics classes, even though my rates were better in chemistry. And then I was just thinking, I'm not gonna take the easy path. I'm gonna go for something that is really puzzling and hard, and I really liked the challenge of physics. And so I went to do physics at first, and I did my first degree. It's about 3 to 4 years, depending on where you are. And so in physics, you study a lot of different things. And then once you have a bachelor degree in physics, you can go into astronomy. I know that some bachelor are physics and astronomy as well, so you can already pick astronomy at the bachelor degree if you're interested. But then at the end of that, I really knew I wanted to be an astronomer because I had done a couple of experience, like laboratory experience with the teacher, and we went to a small observatory and we did everything by ourselves. And it was amazing to actually be hands-on a telescope, using the equipment to see something, take data, and then analyze the data to figure it out, to get the science out of it and understand how things are working. And we were observing stars. We were looking at the colors of the stars, and we had those nice diagram which showed like the cool star, the hot stars, and things like that. And I was amazed how we could do that all by yourself without the help of anyone. And this is what led me to do astronomy afterward.
All right, very cool. Let's dip back into Quebec and see if they have one more question for us. Mr. Benoit's group.
Oui, on aimerait savoir combien ça a pris d'années en tout là, pour étudier, pour devenir astronome comme tu es maintenant.
OK. Donc, combien de temps? Fait que moi, ça m'a pris 3 ans pour un baccalauréat. J'ai fait une maîtrise en 2 ans. J'ai fait un passage accéléré au doctorat. Mon doctorat, je l'ai extensionné. J'ai fait un long doctorat de 6 ans, mais la plupart des gens le font en 3 ans. Par contre, le fait que je l'ai fait en 6 ans, ça m'a permis d'apprendre plus de choses. Fait que quand je suis arrivée sur le marché du travail pour appliquer pour des positions puis des emplois, j'ai obtenu l'emploi ici qui était un emploi très prisé parce que justement, j'avais beaucoup d'expérience. Fait que ça dépend toujours, mais en gros, c'est environ 3 ans baccalauréat, 2 ans de maîtrise, puis 3 ans de doctorat en moyenne. So the question was, how much time did it took me to get my degree in astronomy, my PhD in astronomy? And the answer is that, so I did a bachelor degree, which was 3 years at Laval University. And then after that, I did a master in astronomy, 2 years, which after that followed the doctorate. And I did a long doctorate, actually. I stayed there for 6 years. And most people can do it in 3-4 years. But I did a really extended one, which was actually a good thing for me because I've learned a lot while doing my doctorate. And once I got onto the work market, so when I applied for jobs, they saw all the experience that I had. And this is how I got this position here, which was a really hard position to get, even though I was just a new person in the field and I had no experience outside from my PhD. They decided to hire me.
All right, and Mrs. Milich, you guys have the final question from New Jersey.
All right, go, Christian.
That was pretty quiet. Can you repeat that for us? Maybe a little closer?
Get loud, Christian. You can talk louder.
Hi, I'm Christian, and have you ever seen a red giant?
Oh, okay. A red giant. Have you ever seen a red giant?
Okay, a red giant. So yes, I have observed some red giants. So the red giants are like a star that is evolved. It's like an older star, a little bit older, not quite as old like as a white dwarf. The stars are really fun, have really funny names. But so the red giant is an evolved star that has changed its combustion. So I was telling you earlier that, you know, our sun is burning hydrogen and is creating new elements, new atoms. So a red giant is a star that has burned too much of its hydrogen. And because of that, it started to burn other stuff. And when that happens, the star kind of inflates. It becomes much bigger. So a star that burns hydrogen would be like this size, and then it starts to burn something a little bit heavier like helium, and it becomes bigger because the helium is producing more energy, so it really inflates. So if we would pick the sun, for instance, the sun is not a red giant, but it will eventually become one when it's going to get really old. And when the sun will be a red giant, it will inflate, and its radius, the size of the sun, will actually be bigger than the orbit of the Earth. But don't be worried by it. It won't happen until like 5 giga years. So we won't be here for sure. And we observe them, the red giants, all over the galaxy and in other galaxies as well.
All right, very cool. Well, I want to give a big shout out to our classrooms on YouTube, our classrooms who joined us live on camera today. Thanks as always for hanging out and your awesome questions. And Laurie, thank you so much for hanging out with us today. That was an awesome presentation. There's so much.
It was a lot of fun. Thank you so much.
Yeah, thank you so much for hanging out with us today. The last thing I'm going to do is I'm going to turn on the mic. So boys and girls, if you want to get a little bit loud, a big goodbye and thank you for Laurie, and then we're going to sign off. That part. Again, thank you so much, classrooms. Laurie, that was awesome. Hopefully we can host you again in the future. Maybe we'll do a full-on French event next time. Thanks so much for hanging out with us today.
Awesome. Thanks. That was great. Have a great day.
Thanks,
Bye.
everyone.